Okay, welcome for joining us. My name is Claude Duguay, and I am joined by Ian D'Souza from Honeywell Aerospace through an independent Ethernet connection. And we'll be talking today about Global Water Future water microsatellite mission. So before getting to the details about the concept of satellite mission we have in mind, I would like to provide you a bit with some context as to where this satellite mission would fit under what umbrella. So I'll first start by saying a few words about the Global Water Futures program, a Canada-wide program, and then the Transformative Sensor Technologies and Smart Watersheds, which is a project under Global Water Future. And thirdly, about specifically the water microsatellite mission concept design, which is one component under the TTSW project. And then we'll have a question and answer period, and both Ian and myself will be able to answer some of your questions. The Global Water Future project is under the Canada First Research Excellence Fund, being led by University of Saskatchewan, and in partnership with University of Waterloo, McMaster University, Wilfrid Laurier University, all three universities in Southern Ontario, as well as other partner institutions. Now, the Global Water Future project aims to place Canada as a global leader in water science for cold regions and to address the strategic needs of Canadian economy in adapting to change and managing the risks of uncertain water futures and extreme events. If you want to find out, if you're not familiar with Global Water Future, you can find out all details about the program and the several projects that are supported by Global Water Future at the link provided at the bottom of this slide. Now, the TTSW, Transformative Sensor Technologies and Smart Watersheds, is a project under Global Water Future, and its goal is to develop, improve, and test transformative technologies. So we're talking about smart sensors and sensor networks, including terrestrial sensors, suborbital sensors, UAV and aircraft-based sensors, and satellite remote sensing systems, which will be implemented on a pan-Canadian scale and targeted to support water futures issues throughout cold regions. As part of the TTSW project, we've divided the task into two major work packages. One focuses on terrestrial sensors and smart sensor networks. So the two main objectives are to improve measurements and environmental parameters in cold regions through development improvement in ground-based sensors. And on your right, the picture you're seeing here, this is a sonic sensor being developed by University of Saskatchewan to measure snow depth. Secondly, is to establish a pan-Canadian network of smart hydrological field observatories to support environmental monitoring. The second work package focuses on the use of drones, airborne, and satellite remote sensing observations. And under this, we have three tasks. One is to improve drone platforms and sensors for operation in cold weather. And an example on the right, this is a drone built by a company in Saskatoon, I believe, Dragonfly, which can operate at cold temperatures, and we're talking about temperatures of the order of about -15 degrees. Then the second objective is to improve quantification of snow water equivalent and near surface soil moisture freeze-thaw state. And finally, which directly relates to the satellite mission concept I will be discussing in the next few slides, it's to develop the design concept of a microsatellite water mission. Now, the water microsatellite mission is a multi-pronged solution for water needs. First, what we're looking at is the design of microsatellite mission for freshwater monitoring. Global Water Future being really led by mostly terrestrial hydrologists. The focus is on fresh water, but does not preclude any possible observations over ocean marine environments, and also over terrestrial environments, especially if we look at landscape ecology types of applications. So it is open, although the focus is on fresh water. Secondly, it's to advance water research and support the research community. So the design we have in mind, the satellite, this microsatellite would carry 2 instruments on board. One is an hyperspectral sensor, and the second one is a passive radar reflectometer, or often referred to as GNSS technology, for monitoring several water quality parameters and quantity parameters, rated parameters. Some examples include algae, chlorophyll A, dissolved organic carbon, and water stores in snow, soils, and lakes. The mission would also gather data from hydroelectric field observatories, so sensors deployed as part of a network of sensors through low-cost smart modems, so allowing sensor data to be delivered directly to researchers via internet connections. Now, if we look a bit more at the details about the technology being proposed here, the hyperspectral sensor, it would be at high spatial resolution. The spatial resolution has not been precisely defined yet, but we're certainly looking at spatial resolutions of 100 or 200 meters and better in the tens of meters. The spectral range from visible to near infrared, and again, the specifics of the range will be determined based on the survey, the user requirements. In general, we are looking at wavelengths in the 400 to 1,000 nanometers, and possibilities of going a bit lower in the electromagnetic spectrum, as well as a bit higher in the near infrared and perhaps into the mid-infrared part of the spectrum. The sensor would operate and provide roughly 400 spectral bands. Now, for the GNSS reflectometer, it's been shown in recent studies that there is a sensitivity of the signal. It's an L-band passive radar, sensitive to signal to surface soil moisture, snow on the ground, snow water equivalent, as well as surface water, being 3 areas which has been demonstrated that the potential for GNSS does exist. And finally, the other technology would be on board of the satellite mission would be provide communication, 2-way communication with terrestrial modems, and data would be delivered up to twice a day to the users. Now, when we look at the design of a satellite mission, we have to go through various phases or steps. And we are at present at the first step of the process, where we are defining the user requirements, or called also the science requirements. And in this case, we try to identify what type of data, what type of parameters we'd like to measure, how much, how often, revisit rate. Would we, for some applications, or maybe interest in having acquisitions once every week or once a day. What resolution, the time, the temporal resolution, as well as the spatial resolution, allowable latency, basically the time between data acquisition to delivery to user. Are the users interested in getting data provide to them directly every hour, every 4 hours, once a day? So this is at the stage where we're at right now and where we need your feedback. And following this step, then we will be moving into the definition of the mission objectives, mission requirements, systems requirements, and so on, as you can see on the slides. So so the purpose of this webinar was to present to you the general concept of the site mission we have in mind, and we're really looking for your feedback. So we did produce a survey, which is available online, and it's open until the end of December. The link is provided. And if you want to learn more about specifically about the Transfer Technology Sensor Network project, then you're welcome to visit our website. And this moves us now to the question and answer period. So thank you very much. Ian? Yeah, Ian, do you have anything to add to this, or will you just we'll take questions?
I'm happy to take questions. To add, I think I recognize some of the people who are attending on the conference. I've met them before. The main purpose of this is to sort of assist the Canadian water community, because there are various methods of gathering data. So I might want to add to what Claude has already said about the sensors, or the two sensors are the hyperspectral and the reflectometer. But the third one is a data gathering method, which provides like a very low cost method of bringing back your data from sensors that you might have deployed in the field, especially in remote areas. So you can deploy hundreds of sensors if you have them, connect them to these really low cost portable modems, which have a battery life of about 4 years on 2 AA batteries. And these will talk directly to the satellite. And every so often, or whatever your needs are, will update or upload that requirement to the satellite, and which will download it to an internet connection where you will receive it at your computer. So you could literally have hundreds of sensors in the field, in your watersheds or wherever, and have that data brought to you to your desktop at certain periodic intervals. So other than that, I'm happy to take any questions as well.
Do you want to just read? There's a question from Richard Kelly. You can see Q&A.
Okay, there's a question here. Is the idea to create single microsat or constellation approach? It relates to budget issues.
Right. Do you want me to take that? I mean, the
Yeah,
first
sure.
one is to, I mean, the idea is to first design a concept mission. And you can always add duplicate satellites or more satellites. And right now, it's a single satellite definition. That means you get to revisit over any given area in Canada at least twice a day. Sorry, maybe up to 4 times a day. So 12 hours apart. So 2 visits, and then 12 hours later, another 2 visits. But yeah, definitely we'll bear in mind that there could be a need for multiple satellites, but right now we're designing the single satellite. And maybe I'm not sure if it was clear, but the main purpose of this is to introduce the concept and have users like yourselves go out there and answer the survey of what their current needs are, so we can design appropriately, because otherwise we'll be designing in the blind. That never works. So I'd like to know what users need and what they're doing out there, so to define the satellite parameters or the mission parameters.
Okay, we have another question here. Would it be a radiometer at L-band or active radar at L-band you consider installing? How big is a microsatellite? And are there limitations in terms of size and weight of sensors?
Okay, so there's multiple. Let me just take them one at a time. Right now we're only considering a passive radar. So basically, it's a signal of opportunity. So currently, the GPS satellites are illuminating the Earth at L-band, and so we would be receiving these L-band reflections to determine the status of, say, soil moisture or snow equivalent masses. So right now we're not actually using active radar. It's actually going to be a listen only. The size of a microsatellite is about, you can think of it as a small beer fridge. So it's like a washing machine size thing, and typically about 100 to 150 kilograms. We can go. There's no limitation other than cost to making it be a larger satellite. But definitely there are transition points where you go from a certain cost and then you have a big jump to the next level and to the next level. And launch costs also have to be accounted for, and that will be factored into the whole thing. So a microsat these days is pretty capable. It can do a lot of things, especially with the hyperspectral instrument and the reflectometer. And with the radio receiver that receives from the sensor data, you can go quite far in sort of extending services between the various groups. So when it's cloudy, you can pick up sensor data and so on and so forth. I see some other questions in here.
Yes.
Sorry, but I'm not sure if I answered that question.
Right. The next question was about the bandwidth do you hope to obtain?
So which bandwidth is that are we talking about?
Right. I don't know. I'm not sure what it is. It's a question about the hyperspectral sensor. If it's in relation to hyperspectral sensor, we're talking about roughly 400 spectral bands, and depends really on the range of that we'll be covering, which will define then the bandwidth.
Yeah, so we're talking about optical bandwidth is 400 nanometers to infrared, so 1100 nanometers roughly, that kind of thing.
Yep. Okay, the question was in relation to IoT. So the question, the bandwidth was in relation to IoT.
Right. So the bandwidth that design is optimized now at UHF bands, and there's no limitation. But I can tell you that the limitation, as currently designed, is for 100,000 sensors in the field of view at any given moment. So if the satellite is overhead, you can have up to 100,000 of your sensors, each connected to one of these terminal modems if you wanted to, and satellite could gather all that data and relay it back down. And that's using a very narrow bandwidth because it's been optimized to do this of something like 25 kilohertz in the UHF VHF band. So no pointing is required. You don't need a sensor modem on the ground which has an antenna that needs to point at the satellite. It's just transmitting, and they're all very smart, so they know when to turn on and when to turn off. So I see Kiana has forwarded a question about CSA, and to answer that question is yeah, I mean, of course this will eventually, if this goes forward, will be a CSA mission. I know the CSA maybe they had at one point planned on a WaterSat mission. We don't know what the current status is at the moment, but if what we're trying to do is prepare a mission. So the CSA's mandate is to serve Canada and to serve Canadian government and the Canadian public. And so if this is a requirement of the water researchers across Canada in this GWF program and whoever else may be listening, then certainly we'll take this with the requirements package to the CSA and say, hey, here, look, these guys are interested in something. Do we want to work on this? And so, yeah, of course, we will involve the CSA at some point. But right now, we're in the information gathering stage as to what it is that people need. And we're using the GWF program to sort of help along because there's this gathering automatically. There's this critical mass of researchers available to us to do this information gathering.
Okay, we have a question here about the ground resolution of the L-band, the GNSS instrument. So basically from what would be roughly the size of the footprint on the ground?
The footprint size, so depending on the orbit altitude, we're still working on this instrument. So this is an instrument in progress. We're working with the York University. That footprint size, I cannot tell you right now, but I know that the resolution will be on the order of hundreds or tens of meters, simply because the L-band signal is a few centimeters.
The second question from the same person was asking about the range, if it could go up to the 1.6 micrometers. And my understanding of that, talking to this fellow yesterday, is that it's to facilitate the discrimination between clouds and snow, for example. Because now we're moving into the mid-infrared at 1.6 micrometers.
Yeah, so 1.6 micrometers, I mean, nothing is impossible, but now you're talking about a payload that has to be cryogenically cooled or cooled sensors. So if that's really a vital issue right at the moment, if there's no other way to get around it, then yeah, we can talk about it, but that's part of the trade space that we have to discuss because obviously we'll try to do the best to accommodate the majority, but you know, without driving the cost of the mission into some area where it won't be feasible.
Okay. And the next question is in relation to the orbit of the satellite. Was it going to only cover Canada? Will it be geostationary satellite or sun synchronous?
It'll be a low Earth orbit satellite, and right now we're considering sun synchronous, so it'll be sort of a North Pole, South Pole type orbit. We don't have the local time of the ascending node yet, but it'll typically be like a 10:30 a.m. ascending node. That's a very popular orbit, so the cost of getting a launcher is lower to do that. But typically that's our starting point. If there's any reason to deviate away from there, then we will look at that. But yeah, so we're talking about an altitude of about 650 kilometers rather than geo, which is thousands of kilometers. And also in coverage, yeah, definitely it'll cover Canada, but as the Earth rotates, it'll cover the entire planet. So right now we're focusing on Canada as this is a Canadian mission, but definitely most of the time the spacecraft will be over other places.
Okay, do we have any questions? Yes, there's another question here. To which depth would soil moisture be estimated? With L-band, we're looking at, of course, maybe top 20 centimeters or so. It really depends on the moisture conditions. So we're not looking at definitely at great depths for the moisture estimates, but it's what we call the near surface soil moisture, but with better capabilities and using a C-band instrument. Yeah. So that would be my guess at this point in time, until we do some experiments with one of the instruments actually that Ian was talking about, the GNSS instrument that's being developed by York University. And the plan, if I understand correctly, Ian, is that this will be flown in an aircraft, and there's coincident field measurements, and that a better idea of be able to put a better number on the possible retrieval at what depths.
Yeah, so we're going to do an airborne trial, so probably an aircraft or a helicopter flight over different types of sort of soil moisture, and maybe lakes, and just to look at the differences. But that air trial is going to be in the works. It's the next project that we're working on.
Comment section. The swath and the coverage of the hyperspectral sensor. Did you guys get it?
No, I've not seen. I'm told that there was a question, but it was in a comment section regarding the possible swath of the hyperspectral sensor. So what area would cover in one swath?
Yeah, so all these things are part of the user requirements, because we get in engineering wise, there's nothing stopping people from designing whatever you need. So the purpose of the survey is to ask, what are you looking for? So you want something specific in a swath, which relates obviously to the resolution, because the wider the swath, the more difficult it is to get high resolution. And the narrower the swath, you get better resolution, but then the coverage time to cover various areas will vary. So what we'd really like to hear is, what kind of resolution do you want, and how often do you want this data? And that will play into the design of the instrument.
Do we have any other questions? I don't see any other questions at this point in time. So if there's, I'm not sure. Just something here. Oh yes, so there's another question that just came in. So with the orbital plan, will you get data, will you get Canada-wide coverage in a day or sampling of Canada twice a day? Ian?
Yeah, sorry, I had my microphone muted and I was speaking away.
Apologies.
Yeah, so Richard, yes, but the current plan is the idea is that the satellite will revisit any given, say, city in Canada and any part of it twice a day. So it'll definitely fly over that city in a day, but typically 2 or 3 orbital passes, consecutive passes, will still have a view of the city. So if you say pick any location in Canada, you will get 3 passes, maybe, or maybe 2 passes a day, where it will go over, and then 12 hours later, it'll do the same thing. So as the Earth turns under it, so that orbit remains stationary with respect to the stars, and you will get 2 passes, and then 12 hours later, another 2 passes, and that occurs for every place in Canada. So that's the data acquisition part. And then at some point, the data has to come down. So depending on where the ground stations are, we have to figure out the optimal way of bringing that data back down to ground. So I don't know if you mean you're interested in getting hyperspectral data multiple times a day, or are you looking at sensor data twice or multiple times a day?
Yeah.
Or L-band, yeah.
And as we know, the hyperspectral, when there's of course, darkness at night, then we don't get,
You won't get much. Yeah.
No, we don't get much, but definitely with the GNSS and the sensor network.
Yeah, so we'll play between those things to figure out how to optimize the system, but we can't do any of that without results from the survey, basically.
Yeah. Another question is about timeline to complete the satellite from design to orbit.
Right. So I mean, typically, so we've done this before. We've done other satellite builds, and we've done other sort of baseline mission studies. And we've actually got satellites to orbit. The shortest we've ever done was from concept to launch in 7 months. But that was everything went well, and everything was lucky. But typically, you can count on a 3-year period from when you start your design and build, like what we're doing now, to when you can say you're going to be put on a launcher. Things can speed up depending on how fortunate things are and how how much compromise you're willing to have. Because if you want that perfect launch, then you either have to wait or pay for the ultimate launch, and that's usually one of the hang-ups.
Mm-hmm. Other questions?
From the GWF side of things.
We don't know at this point in time. From the GW side of things, the plan for the launch, it of course it depends on funding. So first of all, we were building the case for this mission. With the help of Honeywell, and then it's to obtain the funding, and once the funding is obtained, then the launch would definitely be possible within the scope of the Global Water Future Program, which runs for 7 years. It started in fall 2016, so which will run probably till September or August 2023. So that's a possibility.
Yeah, I think it's important. I think that I've often got this question, very similar, and somewhere in the mind of the scientists, including myself, is that someone is out there building these satellites, and then poof, you'll be supplied data. But what really happens is that there's a group of scientists who get together and say, "Hey, wouldn't it be great if we had this kind of data?" And then they approach the engineering teams, and they come up with this design concept for an instrument and a mission that does that. And then you approach a funding body, and with your idea, and especially if it's a government body like the CSA, where there is a benefit for what they're doing to the country or maybe to the world, then you start this program of building a satellite and launching it and getting data service from it. But it never happens that the CSA will come up with its own design off a satellite and launch it and then be supplying data. That doesn't happen. It has to be the science community that comes together first and says, this is what we need. And, then we go ahead and build it.
No quick questions regarding whether the data will be open source.
And yeah, I mean, there's no reason. So that's all part of the CSA model. So when whoever's paying for this thing will determine the source. So from Honeywell's point of view, it's the idea is to just build and launch the satellite, and that's where the money's coming from. But the data itself is whoever owns the satellite. So Honeywell will not own the satellite. So if it's the CSA or some other government department like Environment Canada or whoever who has actually paid for it, will own the data. It's up to them to distribute this data at will. And typically, science data is distributed free of charge.
Yeah, the one question here, it's in someone asking in the room, whether the data from terrestrial sensor network, where would it go? Would it go to the researcher? I think, but I think that's part of the questionnaire, actually, the survey we have online. We have questions regarding even the researchers who deploy their instruments in the field, whether they want to make their data available or not.
Yeah, so it's up to entirely the researcher. So right now, the model that so we're not designing that. So there's another company that we're aware of that does this. The model is, you go in and get these modems, and they're uniquely identified, and it's up to you to decide whether you want to have that data available to everybody or just brought back to yourself. That's entirely your prerogative, and so it depends on what if it's typically like someone monitoring a lake, and they need the data to be available to multiple parties, then it's typically for everyone. But this doesn't necessarily restrict to water. If you're a farmer looking at cows in your field or something like that, you may just want that data yourself. So there's no limitations of what the sensor is. This is just the modem relay, which is about the size of a credit card. That will be attached to your sensor that'll talk directly to the satellite.
There is a question, I'm told, in the comments section, and which
I see a timeline. That data is open source. I don't see any other question. Oh. No, in the chat.
Yeah, in the chat.
Oh, sorry, yeah. Oh, from Armagon. Yeah, hi, Armagon. So she's asking, I was wondering if you could tell me about the GNSS payload. Do you use GNSS to estimate dialectic part? Yeah, so right now the payload, all it does is looking at the reflections from the GPS signals from the Earth. And right now we have a postdoc working on the signal interpretation and algorithms. And yeah, of course, dielectric properties are being determined, and trying to determine the signature of different types of soils is part of the whole algorithm development.
And I think one of the novel things about the mission is, of course, the fact that we can acquire the hyperspectral data imagery, a GNSS signal, and some measurements from the field instruments. So if someone, for example, is thinking about, let's say, using hyperspectral data to or some bands with the hyperspectral sensor to retrieve, let's say, chlorophyll A, in a lake. If you have a buoy that actually measures also chlorophyll A, you'll be able to have simultaneous measurements. So one interesting aspect of this is that one could even think about running. You have an algorithm. You're running your algorithm, and you'd be able to do some validation of that algorithm, and then also some improvement and development of algorithm based on the data that would be acquired at some of these instruments as part of the observatories. So that's one example is chlorophyll A, but one could think also about let's say, snow water equivalent measured, or snow depth measured at a met station or a group of met stations, and where one could look at the relation between the signal obtained with GNSS over that study area and the measurements of snow depth from these sensors deployed in the field. And that could be done, you know, on more than once a day, actually. Do we have other questions? Okay. Yeah, if not, then I'd like to remind you that we have the survey online. So this presentation is available. And you just click on the link to the survey. The survey takes about 10 minutes to complete. Many are just, you know, you click the the button, and there's at the end there's a little comment box. If you want to add additional comments, you're welcome to do that and submit. So thank you very much for your time, and we're looking forward to working with you. Bye-bye.